So let us start, students. Okay. So let us go with next one. Is very important. It's called fin. Okay. So sometimes to account for the fins. Okay. Sometimes what happens, the tube are finned on one side. Okay. So we have seen about heat transfer coefficient. The areas are there. Okay. So in some cases, in some cases, the surfaces surfaces inside or outside surface is finned to increase the heat transfer rates. Now, in such cases, in such cases, such cases, the finned surface area, finned surface area, AS, which can be AI or A naught, can be expressed as can be expressed as AS is equal to A total, which is given as A fin plus A unfin. Sometimes we use efficiency of the fin. Okay. Also, taking into effect, taking into consideration the fin efficiency. You know what is fin efficiency, is it not? AS is equal to A fin plus A fin, sorry, A unfinned area unfinned plus efficiency of the fin into A of the. S can be internal or external. Done. Next one we will see fouling, which is very important. I'm putting all these things for theory basis because sometimes you may get a theory question. So in theory questions, if you understand theory, at least 20 marks can be increased every subject. See, 20 marks theory will be there generally in GATE. If you see the old GATE papers, you will see at least 20 marks theory will be there. So just if you know theory of all the subjects, 20 marks can be scored. Is it not? Yeah, maximum 80% is problems only in GATE. I do agree. But 20 marks is it? 20 marks in GATE. Okay. Now, fouling. Fouling. You know what is fouling, is it not? What is fouling? Fouling is accumulation of accumulation accumulation of deposits on heat transfer surfaces. Heat transfer surfaces causes causes additional resistance to heat transfer, causes additional resistance to heat transfer. Uh, additional resistance to heat transfer. Okay. So common fouling types. Okay, fouling types of fouling. First type is called precipitation fouling. Precipitation fouling. The solid deposits which are there, okay, which is on the inside the inside the fluids. For example, in water, if you see, if you use steel surfaces, okay, anything, for example, in baldi agli, ಇಲ್ಲ ನಿಮ್ಮ ಯಾವುದಾದ್ರೂ steel ಕಕಟೋರ, you don't clean it for a long time. You use water only. Okay, you boiling pot which boils only water. Okay, you see after some time there is some deposits which is there, which is generally the calcium deposit which is there, which if you scratch it will come out. See that? After a long time you leave it just like that, what will happen? Okay, it will form thicker layers which by scratching only it will not come. Those calcium deposits will be there on the surface, which will reduce the heat transfer rate. Understand? When you put copper to anything, what will happen? It will increase the heat transfer rate. But if you put, that's why copper bottoms are put, is it not? It will increase the heat transfer. But if you put these calcium deposit, it will decrease the heat transfer rates. So that is called fouling. That is called precipitation fouling. Okay, where deposits from the which is there already in the mixed in the fluid precipitates. Okay, so solids that are mixed or dissolved inside liquids precipitate. It not need not be liquids also, it can be gases also, or liquids or gases, dissolved inside liquids or carried by gases, or carried by gases precipitate on surfaces. Correct? It precipitates on the surfaces. Example maybe smoke hogo chimney alli, you'll see those carbon deposit on the chimney where the smoke is going out, is it not? So it might be good, it might be bad, but sometimes what happens in boilers, okay, these deposits are very bad because you need to increase the heat transfer rate. So these deposits are very bad. Okay. You may see, nowadays we don't use these pots. ಅಂಡೆ ಬಿಸಿ ಮಾಡಿಕೊಂಡು ಮನೆ ಅಂಡೆ ಉಂಟು, ಯಾರ ಮನೇಲಿ ಅಂಡೆ ಇದೆ, ಮಂಡೆ ಅಂತ ಹೇಳೋದು. ಅಂಡೆ 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 ಇಟ್ಟರೆ ಅದ್ರ ಮೇಲೆ if you do it using firewood, if you see, there'll be deposits on the other side, the carbon deposit. This is flue gases which is carrying those carbon deposits, and that is called precipitation fouling. Okay, where you have the deposits on the surfaces. Okay, so this happens also in our boilers. So there are ways to avoid it. So that is precipitation fouling. Second one is chemical fouling. Okay, chemical fouling. Chemical fouling. Chemical fouling is accumulation of chemical reactants some reactive elements are there which forms something. So some chemicals which gets which is accumulated over the surface. Okay, this kind of accumulation can be avoided by coating pipes with glass or plastic pipes. Okay, so what happens? Accumulation. This might be rusting also. Rusting is also a chemical process, is it not? So that or corrosion maybe it influences that particular material. So the fluid which is going is chemically reacting with the pipe surface, and it is forming that chemical coat. To avoid this, chemical, to avoid chemical fouling, chemical fouling, to avoid chemical fouling, to avoid chemical fouling, metal pipes, metal pipes are coated with glass or plastics. With glass or plastics. Now, if you put glass or plastics, will it not affect the heat transfer rate? Of course, it does. You put glass or plastics, glass and plastic have low heat transfer rates, or sorry, conductivity. Okay, so because it has low conductivity, will it not affect the heat transfer rate? Of course, it does. But the thing is that we have to have always a economics perspective here. Okay, which is better? Okay, heat transfer rate, what is coming, what is the cost of lowering the heat transfer rate, and what is the cost of having it corroded. The both things have to be seen, and then the decision has to be taken. See, critical thickness of insulation, yes, we can use it, but the thing is that, see, it depends on, see, we have to understand. uh, Yeah, we can use it. I'm not saying no. Okay, that is to increase the heat transfer rate. Of course, we can do it. Okay, so critical thickness of things is very important. But then, where is the chemical fouling happening? Whether it's inside or outside. Okay, if it is outside, then what you said is right. You can use critical thickness of insulation. But here, what is happening inside? It's becoming lower. Heat transfer rates are reducing. Outside, what happens? Convective heat transfer rates are increasing when you put insulation. Is it not? So that is why the heat transfer rate increases. In the inside surfaces, by putting this, heat transfer rate has only to reduce. It cannot increase. Yes or no? So when you say critical thickness of insulation or critical radius, if you see here, if you clad this with the insulation here like this, you're cladding this with insulation. So why is that when you clad it with the insulation, there is more heat transfer rate happening? Because there's more surface area for convection. But if you say inside part, if you clad, what is happening? Heat transfer rate is reducing because the area for heat transfer is reducing. Convective heat transfer is reducing. So there is no question of critical thickness of insulation for internal flows. Is it not? It's only for the external flows. This kind of thinking has to be there. What is the reason for critical thickness of insulation being there? Has to be revised. Okay, sure. Next, third one, which is there, is called biological fouling. Because sometimes these chemicals or anything will be, or water will be at 40 degrees, 50 degrees centigrade. At this 40, 50 degrees centigrade, what will happen is there will be algae which develops. Okay, they reproduce, and then that algae is formed all the places. Okay, that is called biological fouling. Okay. Biologic fouling is yeah, heat fouled by the growth of algae, growth of algae in warm fluids. You know, these algae are increased, the production rate of the algae. will be increased when it is around 40 degree, 45 degree, 50 degree, that range. And generally when you say hot water with this 30, 40, 50 degrees, then not 30, around 40, 50 degrees, then this algae growth is happening. So that growth has to be removed. This is another fouling. Okay, that can be used by chemical treatment, can be avoided by chemical treatment, can be avoided or can be prevented by chemical treatments, various chemical treatments. Chemical treatments. Okay. Now, what happens because of this? Okay. What is the main uh, now there's something called fouling factor. Okay, fouling factor is represented as RF. Okay, which is resistance per unit area, which is increased. Increase in resistance per unit surface area. Okay. So we have you written this down? Finish. Now we have there is something called fouling factor. Previous slide. Done. So very important students. Okay, because heat exchanger is generally used in almost every industries. Okay. So fouling factor RF is resistance to heat transfer added because of fouling, fouling, fouling per unit surface area, per unit. No, wait a minute. It's not per unit surface area. Just a second, do not write. Yeah, that this resistance to heat transfer added because of fouling enough. The whole, the whole surface area, that is what it is. Okay. Okay. Yeah. The resistance to heat transfer added. Okay. So now generally what happens is, okay, fouling factor is zero. RF is zero for new heat exchangers, and increases with the time, and increases with the time, of course. Okay. Now fouling factor RF depends upon depends on the operating temperature, the operating temperature and the velocity of the fluids. Okay. Another thing, fouling RF increases with increasing temperature and decreasing velocity. So velocity is increased, fouling reduces. Of course, these are all common things which you know, is it not? It's not something which you don't know. Now, generally, what happens if there are both sides, the fouling happens, then what happens? You can write 1 by UA at any surface is equal to 1 by UA at I, UI is equal to 1 by U naught A naught can be equal to total R, which can be 1 by HI EI plus the fouling resistance RF inside divided by area of the inner surface, very important, plus log of this area is very important, we missed that out. Okay, log of d naught by di divided by 2 pi kl plus rf of naught, that is outside, by a naught plus 1 by h naught a naught. Makes sense? So see how rf is used. Rf of naught. Okay, so that is how fouling resistance is used. So there are different types of, then the RF, the unit is RF unit is meter square Kelvin per watt. Very important. Meter square Kelvin per watt. Yeah. See, RF is the total resistance which is there all over the area. How much is deposited? Divide by area if you do, only then you get. So RF, when you say meter square, so meter square Kelvin per watt. That's how RF is taken. That's how it is taken. We could have used other way also, but we have to go with the convention. Is it? What is fouling factor? How it is defined? That's how we have to. Now let us analyze heat exchangers one by one. Fine. So this is very important. First, has been asked, okay, or can be asked. Okay. So next, analysis of heat exchangers. Very important, students. I am going slow, and with the purpose. I am going slow with the purpose. Okay. So let us see. See, generally, what happens, there might be counter flow, cross flow, whatever be the type of flow which is there. One of the things we have to get is Q, right? Q is the heat transfer rate. Heat transfer rate can also be given as, see, if you say heat transfer rate, heat transfer rate, okay, heat transfer rates can be given as, okay, heat transfer rate or in a fluid, in a say hot fluid or a cold fluid, in a cold fluid, let us say cold fluid can be given as, can be given as q dot is equal to m dot cp, constant pressure. Okay, the heat capacity at constant pressure or specific heat at constant pressure into temperature of the cold fluid which is going out minus T of cold fluid which is going in, right? This can also be equal to, so Q dot is also equal to, because from hot fluid it is going to the cold fluid it is going to hot fluid, right? So this can also be equal to MCPC, I will write. MCPC. C means cold fluid. Okay. So Heat transfer rate, this capacity, heat capacity, specific heat may be different for both of them. Okay, it depends on what is the purpose of doing. Okay, so next, it can be m dot cp. Okay, for a hot fluid, for a hot fluid, heat transfer rate must be same as the cold one, must be same as the cold one, right? Heat transfer rate must be same as the cold one, and is given as and is given as q dot. I am not saying the direction of heat transfer. Okay, it is m dot. This I will say c here. Let write c here. M dot h into m dot, sorry, c dot or cp comma h into t h in minus t h out. Yes or no? Temperature of the hot fluid which is coming in minus temperature of the hot fluid which is going out. Is it not? So here you know all the things. This is yeah, these are outlet temperatures, these are inlet temperatures, right? So whatever be the case, whether it's counter flow, cross flow, or any type of flow, this is applicable, is it not? What is the equation now? Last we used, we should not miss it. This is 2, is it not? So let this be 3. Let this be 3. The fin and unfin, okay, and let this be 4. H, and let this be 5 and 6. And those both should be equal, is it not? Now, sometimes we say something called heat capacity. Heat capacity rates for hot fluid, say capital CH, and cold fluid, capital C is defined as CH is equal to CH is equal to m dot H CP and CC is equal to m dot C CPC. So write this as 7. This is called the heat capacity rates. Very important. Now, here we have to understand a bit more. Okay, more of intuitive understanding is involved here. Okay. Fine. Now here, in case the heat capacity rate is high, then the temperature difference will be low. Correct? T H in and T H out. You consider heat capacity rates are high, then the temperature difference between starting and ending will be low. If the heat capacity rate is low, the temperature difference is high. This understanding has to be right. Because, see, here I'll write this down. Have you written this down? Finished? No. Understand properly. Heat capacity rate is high. Temperature difference between in and out of a fluid will be low. Okay. If you have water one side and then other side we have other fluid which has lesser heat capacity, maybe oils. Oil has lesser heat capacity than water, is it not? So where the temperature difference would be more, where the heat capacity is less. Make sense? Right. See, in a heat exchanger, very important note, in a heat, not heat, its temperature will be losing fast, will drop fast. Okay, the one which has lower heat capacity rate, either because of m dot or because of cp. Two things are there. It is not just cp alone, it is the flow rate also. If the flow rate is slow, then what happens? Temperature rise will be more. If the flow rate is more, the temperature rise will be less. Make sense? Similar with cp also. So what accounts m dot as well as cp together. So that is why heat capacity rates we are talking about, right? So in a heat exchanger, the fluid, the fluid that that possesses higher heat capacity rate undergoes 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 lower temperature change, lower temperature change between the inlet and outlet. And similarly, similarly, the fluid that possesses the fluid that possesses lower heat capacity rate, lower heat capacity rate undergoes higher temperature change. And heat capacity is the multiplication of m dot as well as cp, both together. Fine. Now, so we can write q is equal to q dot is equal to ch into th in minus th out, and this is also equal to cc into tc out, minus tc in. It's the same. Now if of one of the fluid if one of the fluid undergoes a phase change, where does this happen? In the condenser, in the evaporator, there is a phase change which is happening, is it not? Phase change, as in condenser or evaporators, as in condenser or evaporators. Q dot is equal to m dot into hfg. Very good. So this would be equation number 7 is over 8, and this is 9. Very important. So it's not always this. Sometimes it may condense or it may evaporate, both cases. temperature difference is not there at all, is it not? When something is boiling, does temperature change? No, it does not. Correct. Water boils at 100 degrees centigrade from water to steam, right? So you have steam at 100 degrees centigrade and water at 100 degrees centigrade. Correct. This is ninth one. Write it down neatly. Don't worry. This is very important. And also, 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 Q dot is equal to U A surface, any surface, into delta T mean. Now the purpose is to find out this delta T mean. See, you may do this T in, T out and all those things, but still, another way is to find out the log mean temperature or the temperature difference. Okay. So how to find out this T mean is important. Okay. One of the way to find out this T mean is our log mean temperature difference. Done. Now, one of the ways is having a log mean temperature difference, is it not? So let us look at log mean temperature difference. The log mean temperature difference method, or LMTD method we call it. Let us look at LMTD method. Okay. So let us take a parallel flow heat exchanger. Let us take a parallel flow heat exchanger. So if I consider the parallel flow heat exchanger, what will happen? You will have the over here, right? This is our parallel flow heat exchange. Here we get cold fluid in, cold out. Here we'll have hot in, and hot out. Correct. This is how parallel flow heat exchanger is there, right? So if that is the case, what will happen is hot fluid, if you consider, the temperature will go down like this, and cold fluid temperature will go up, right? So if I say this is TH in, this is TC in, this is TH out, and this is TC out. Okay. Now let us say this distance here, okay, let it be there, that we will not say. Okay. Now let us take a small area dq. So heat transfer is happening in a small area. Let us say this is AS, surface area. Now let us take this one. So we have a hot fluid, okay, which is losing heat to this, is it not? So there is all the things going like this, all of them. And let us say this is DAS, DA surface. Okay. Yes. correct? So let us say that surface area is that. Okay. So along that surface area, okay, if I say there is a m dot which is going, okay, along that area DAS, small a, the considering the small area dA, considering the small area in the heat exchanger DAS, DAS, okay, we can write dq or delta q, because dq you cannot write, right? Because it is of dq is equal to minus m dot h cph into dth, and dq is also equal to m dot c cpc into dtc. Correct? How much heat is transferred. Now this means I can write, since therefore I can write from here, I can write this as, say this is, okay, let me, then I can write dth is equal to minus of dq divided by m dot h cph, and dtc is equal to dq divided by m dot c cpc. You can write this, is it not? Simple analysis. Okay, very very simple. So when we go like this step by step, students, things become very easy. Is it not? Done. Okay. Next. Now, not over. Correct. Write it neatly, students. Today evening class, Murli sir's class is also doubtful. Okay. Just told there is doubt. So prepare mentally for that also. My class, of course, is not there. Okay. Not up, not up. No. 4 o'clock class is there. Ah, yes. After buckling, 1 hour 15 minutes I will take. Then I leave. Done. Okay, next one. See now if I see, say dth minus dtc can be written as equal to dth minus dtc can be written as, okay, minus dq dq dot dq dot into 1 by m dot cph plus 1 by m dot cpc. Can I write it like this? dth minus dtc. Can I write it this way? Correct. Or this can also be equal to, this can be equal to d of change of th minus tc. This is very important, students, so I'll put 11 because this helps in analyzing, doing problems, this particular equation. So also also since since dq dq dot can be equal to u times das into th minus tc, th minus tc, correct. So we can write d of th minus tc divided by d of th minus tc divided by divided by th minus tc is equal to minus u das into 1 by m dot cph plus 1 by m dot, here we have to write m dot h. I'm very sorry, I missed that m dot h and m dot c. M dot h cph and m dot c cpc. Right? Makes sense. When you're integrating, what do we obtain? Log of th out, integrating between inlet and integrating between inlet and outlet, inlet between inlet of the heat exchanger to the outlet, inlet of the heat exchanger to the outlet. I can write log of th out minus tc out. This is very very important, students. tc out divided by th in minus tc in, right, is equal to minus u into a into 1 by m dot h cph plus 1 by m dot c cpc. Correct? Very 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 important. Okay. Now, based on overall heat transfer coefficient, based on the area, based on m dot h and m dot c, cph and cpc, I can get the LMTD. What is this? This is the LMTD, right? So now this you write it as equation number 12. Very important. This is the log mean temperature difference, is it not? Minus comes out, is it not? See, this dH is minus dQ dot, is it not? dH is minus dq dot, is it not? It's losing heat, is it not? Change in temperature is T2 minus T1. Yeah, T2 minus T1 is always negative. Yeah, what is the slope here? What slope is always negative, is it not? Fine. Clear on that or not? One is minus, one is plus because temperature of the cold fluid. So done. This one is done. So next, write it down. Done. Okay. So now this not done. Please write down. Okay. So now see we know that, okay, just understood this. This is understood. We know that we know that m dot c into cpc into or q. We know that q is equal to q dot is equal to m dot c m dot c into cpc into tc out minus tc in, right? And if I consider q dot is also equal to m dot c m dot h cph into t c th in minus th out, correct? Now from these if you see, okay, we have to write what is m dot cph, right? So if I, okay, if I draw here, if I see here, what is m dot c cpc, then m dot c cpc is actually equal to q dot divided by tc out minus tc in, right? Similarly, and m dot h m dot h cph is equal to q dot divided by th in minus th out, correct? Now substituting in equation 12, substituting in equation 12 we obtain, substituting in equation 12 we obtain log of th out minus tc out. Th out minus tc out divided by th in minus tc in is equal to, okay, th in minus tc in is equal to, here I can write minus u as into q dot divided by tc out minus tc in, okay, tc out minus tc in plus q dot divided by q dot divided by q dot divided by, oh, I'm sorry, mc we have to say ulta very simple. So this would be um, tc out minus tc in, tc out minus tc in divided by q dot plus th in minus th out divided by q dot. Make sense? Now this q dot can go on this side. Okay. Taking th in minus tc in is equal to t1 and th out minus tc out as, or not t1, let us take it delta t1 and tc out minus th out minus tc out is delta t2. Okay. Now here you see the q dot is the same, q dot is the same, understand, q dot is the same, just understand, 2 minutes, then I will tell you this q dot is the same. Here th out minus tc out is delta t2, th in minus tc in, th in minus tc in is delta t1. So I can have log delta t2 divided by log delta t2 by delta t1. Here in this case, observe tc out minus tc out, sorry, tc in minus th in, I can take this, okay, let us take this way. So I'll write, wait a minute, students. Th in is positive, minus Tc in I will take, which is delta T1. And here I will take minus of Th out minus Tc out. That will give delta T2. So this whole thing can be changed as delta T1 minus delta T2. Makes sense? So rearrangement I'll write in the next. Right. Tomorrow we will complete heat exchange. From Thursday we will go with radiation. Today I'm not able to pitch in when Murli sir is not there, but sometimes next time when they do, I'll pitch in when Murli sir is not there. So at this time, don't waste time, revise. You will become more and more wise when you revise. And the vice of not revising, you have to avoid. You know what is mean by vice? VICE, vice, bad habit. VICE is bad habit, vice. Vices, drinking alcohol, smoking cigarettes are all vices. VICES, vices. So, vice means bad habit. Sometimes I'll give you some English also. So you will be wise. Wise. It's not wise. It's wise. Wise. When you revise. You'll be wise when you revise. Don't have a vice of not revising. Yeah, sure. Yeah, no, no. Murali's class may be there. It's may. I'm not saying it is not there. It's may be there. But most of the time when sir says it is doubtful, it was generally not there. This is a general experience, but this today it might be a new experience. You don't know. Be prepared for that. That's it. Okay. At least mentally be prepared for the other side also. Okay, it's fine. Done. So I can say it. So I can say here. ಆಯ್ತಾ ಬರುತ್ತೆ ಗಡಿಬಿಡಿ ಗಡಿಬಿಡಿಯನ್ನು ಬಿಡಿಬಿಡಿ ಆಯ್ತಾ ಈಗ so this one will come as I can write therefore by rearranging we can write we can write q dot is equal to u area of the surface can be inside surface outside surface both. Okay, u into area of surface into, but u changes if it is an inside surface. U changes. I'll say us. Better we use us because it can be surface, any surface it can be, is it not? So let us change it to us. It can be inside surface, it can be outside surface. So let us have it us. Okay, us is into log of log of log of, sorry sir, not log. I can write delta T1 minus delta T2 divided by log of delta T1 by delta T. And this we can write Q dot is equal to U dot AS into delta T log mean, or that can also be equal to U naught, sorry, not U naught, US US AS into LMTD, log mean temperature difference. Okay? Where delta TLM is equal to LMTD is equal to delta T1 minus delta T2 divided by log of delta T1 divided by delta T. Very, very, very important this is. Okay, so you get the heat transfer rate. So what is the number we have till now? We have till now 12 is over. Okay, so uh, 12 is over. Let us have this as 13. Let us have this as 14. Where delta T1 is equal to TH in minus TH out, and delta T2 is equal to TH out. Sorry, this is TC in. I'm sorry. Very important. So don't confuse. I confuse generally, so don't get confused with this. When I confuse, help me out. Okay, TH out minus TH in, TC in. Sorry, TC out and TC out. The difference. What is that difference? It is coming here. Observe. This is delta T1. This one goes as delta T1. What is coming this side? And this one goes as delta T2. Makes sense? So when you draw it, you get it properly. Similar thing we use in counter flow. This is parallel flow. So same thing is used in counter flow. Counter flow, delta T1, delta T2 changes. Okay. So for counter flow heat exchanger, right, no? Right. Finished? Finished, bulb? For the counter flow heat exchanger, also the same thing holds true. Understood? There has to be some time for processing, and this is very important because this is important to our problem, right? If you understand it here, you understand it. That's it. You don't have extra revising time. You have less, is it not? So as much as possible, understand in the classes. Online students, any doubts here? Ha, ha, ha. Yeah, any doubts here, online students?
No, sir.
No, very good. Nihal has come. Yeah. Aita. Sir. ಈಗ counter flow heat exchanger same equation. But what is delta T in and delta T1 and delta T out changes. That's it. Okay. Then yes. Now, if you consider counterflow for counterflow heat exchanger, counter flow heat exchangers, same thing, same derivation. Counterflow heat exchangers. You have. So counterflow heat exchanger is like this. You have this as temperature. Okay. This is X as it goes. So you can have the counterflow heat exchanger. Hot fluid going in, cold hot fluid going out. Okay. But then the direction of the flow is changed. Direction of the flow is changed. Right. So here, hot in, hot out. Here we will have cold in and we have cold out. Correct. Counter flow. So what's going to happen? You're going to have you're going to have hot in and cold out. Hot in is going coming here and then it comes down like this and it goes in this direction. Correct. And cold fluid is going in this direction. It's heated. Delta T may be same, may not be same. We don't know. Okay. So it can change. It may not. Okay. So this is TH in. This is TC out. This is TH out. This is TC in. Okay. So here, this one would be where the hot fluid is going in. This difference. Yeah, yeah. This difference is called T1. Okay. And this difference is called T2 or delta T1. This is delta T1, which is given as TH in minus TC out. This is delta T, delta T 2. Okay. So here, one of the things what happens here is, okay, in this thing, uh, okay. Now, what happens here is for counterflow heat exchanger, the same equation that is used for for uh, for parallel flow heat exchanger, that is equation 14 is applicable with a change that delta T1 is equal to TH in minus TC out. Let us write it this as 15, and delta T2 is equal to TH out minus TC in. This is equation 60. Same equation, no difference. Same equation 14 is applicable. How can both be negative? We are not worried about slope. We are worried about what is delta T1 and delta T. Both are positive. It may so happen that delta T1 becomes equal to delta T2. Then what happens we will see. If delta T1 becomes equal to delta T2, then what happens? We'll see. That limiting case we will see. But generally this is the case. Is it not? So further we will go much more in the next class. X-axis is the length or the area or the length, we can say, or the x. We can take x starting from here 0. So you say x here. X need not be how the hot fluid goes. It can be anything. Clear. We'll stop it here, students. We'll stop the recording.